Well, welcome everyone. I'll let Jess introduce himself. But I'm gonna start out first. Hi everyone, I'm Melissa Girmscheid. For those that don't know me, I am currently a ninth grade physics teacher in the suburbs of Phoenix, Arizona, and have been teaching. See, this is year 17. And I've been leading these workshops and developing the resources for computational modeling with alongside Jess since 2017.
Mhm.
Jess?
And I'm Jess Dykes. I teach at Ridley High School, as you just heard. If you heard me talking to Bob, Bob Schwartz is there. He was my cooperating teacher back a long time ago. And I've been doing modeling instruction since 2004. This is my 25th year teaching. And like Melissa said, we've been working together on this for, gosh, 7 or 8 years now.
Yeah.
This is pretty
Yeah.
much taken over our life to a certain extent.
Pretty much. All right, so we're gonna have you guys do some work today. I mean, it wouldn't be AMTA if we didn't have you do some thinking. But we want to kind of give you a little bit of an intro. We're going to examine one of the units that we normally do within like an introductory physics course and see what everyone currently does and how computational modeling puts maybe a shift to what might be currently happening. Um, just want to put it out there that computational modeling came out of this need to integrate more computational thinking into the physics curricula. Um, we know that with the advent of NGSS, using mathematics and computational thinking is one of those science and engineering practices. It is something that, as a part of our increasingly technological society, it's important for our students to understand how these things work, how a machine might think, and how they can use those ideas to kind of drive their own thinking. Jess, anything to add?
Nope.
Awesome. All right. So, a lot of this comes out of a NSF grant that the AMTA was part of back in 2016. Um, has been a grant off and on since then. And there were a few things that were identified as really being kind of an issue within not just physics instruction, but physics first instruction specifically. And one of the big problems that you saw that is a lot of our kids, especially those ninth graders, 14 and 15-year-olds, really had trouble kind of getting the model deployment portion. Doing the experiments and developing a model is is pretty I wouldn't say easy, but it is part of the process for them. Going through and doing an experiment, they're really interested in, but deploying that model and then using it, especially when we're talking about ninth grade, where their algebra level isn't as high as they might use in, say, a mechanics course. We wanted to make sure that we kind of looked at that model deployment and twist that a little bit to make it a little bit more relevant for our ninth graders. And the fact that there was just everything on paper for them didn't make it as interesting as it could be. And so, computational modeling physics first with Bootstrap, I'll say the full name there, kind of came out of this need to address those two issues, that everything was on paper for 14 and 15-year-olds, so you constantly have worksheets, and that they were having this difficulty kind of getting into the model deployment phase of the modeling cycle. And also, big issue, we want to make sure that we're integrating that technology more, addressing, like I said, that science and engineering practice of using mathematics and computational thinking. And I know that working with a lot of science teachers, that computational thinking part of it, when the NGSS came out, was um, there was an immediate reaction that was, I don't know what to do with that. And so this is really the start. I envision that we're going to see computational thinking, computational modeling trickle throughout all of the content areas that AMTA currently has resources for, and also develop some additional ones. All right. So we're going to dive into the constant velocity particle model, and hopefully this works. So if this video looks a little weird, you are looking at a simulated version. So if it looks like if your eyes are good enough to see that the wheels are not spinning, there's a reason for that. But we wanted to use this because we know that this is a very common lab for physics teachers to use. And we have our little tumble buggy moving across the surface. You're gathering data for this. And one thing that we wanted to do to start, and you are welcome to raise hands, chime in, and pop into the chat these three questions. So, when you are doing a lab like this, what is your current process? What are the students examining in the lab? What is the goal? What representations would come from this lab? So, I'm going to give you some time to kind of think about it. And when you're ready, feel free to start popping stuff into the chat, raising your hands, or just unmuting and chiming in.
Sarah jumped into chat with identifying variables, things they can measure.
So I know that we're not quite in workshop, but I'm going to put you somewhat in student mode too. So if we're talking that, what exactly would you measure? What could we measure in that? I see Charlie bringing up the end goal being claim evidence reasoning for colliding buggies that uses simulation evidence.
Charlie is a ringer here, though, just so everybody knows. He's been doing some computational stuff on his own for a couple years now.
Yeah, I'll try not to answer that last question.
All right, I'm going to give everyone, I'm going to about 20 more seconds just in case somebody's typing. All right, position versus time graph, carts of different speeds, the relationship between different variables I see. All right. So if you're one of my students or Jess's, we're going to have you collect the position information for the buggies. And to do that, you'll be listening to a metronome tick every 2 seconds. So students are really collecting, they're marking the position of the buggy every time they hear that tick. So position for every 2 seconds. I'm going to tell you, I do have some whiteboards for my students in here. Keep in mind that they are 14 and 15-year-olds, and these were taken early in the semester. So if you see some 14, 15-year-old mistakes, just know that they were in context pretty darn good for some of them. Okay, so we're looking at, imagine that you have just collected data for this. We're looking at position for every tick, mind you, every 2 seconds. And so we're going to conduct, and once we have collected all this data, go ahead and do a whiteboard session where we're looking at the position of the buggy for every tick, every 2 seconds. And so I have classmates that create whiteboards that look something like this. We could see a distinct difference between maybe the one on the left and the one on the right. But this is our whiteboard discussion, looking at the position for every tick. Jess, anything I need to add here? Can you think of?
The only thing I would add is the process we use. We generally use receipt tape and markers so that they get the positions marked on the paper and it doesn't get messed up if they trip over it, as 14-year-olds will do sometimes.
All right. So ultimately, we want our students to take this information and kind of recreate this motion. So initially, it's looking for patterns within the data and making predictions for information they don't have. So if they're looking at the position of the buggy for every tick, every 2 seconds, for a total of 10 ticks, we're looking for how do I extend out from there? So I want to point out at this point that students they've collected information, just like Jess said, on the receipt tape. They have formed some representations of their own, which we saw in the previous slides. They've now started to create some state diagrams and make some predictions. We have not done any graphing whatsoever at this point. So that's kind of where we are up to this point. And here's where we want to really get into, the meat and potatoes here. So if we're going to recreate this motion, ultimately, we want to create some sort of model using computational representations. All right. So we're going to have them design a function. Let's see. Jess, do you have some breakout rooms ready?
All you got to do is say the magic word. But before you go, if you
Yeah.
look to the right in the chat, the link to the file that Melissa has just shared there for the design recipe is available for you. It's set up where you can view. If you want to write on it yourself, you're going to have to make a copy to make it your own. But the rooms
Okay.
are ready to go, although we
Are they
just
ready to go? Okay, give me 1 second. So what I'm going to have you do is I am going to have you, I have a question for you that is going, sorry, I'm copying the link as I speak as well. I'm going to have you take a look at, you have Jess's there. I'm going to have you start in this one that I'm putting in the chat right now that is a Google Slides presentation, and have you answer a question in there. So it's going to give you some information about what you've done. We're going to create this language that our students use is a function-based language. So we're going to create a function just in thinking, yep, just like that. And thinking on this note with a function that students at this point know has to have inputs and an output. So they know that they know this idea of input and output to a function. We're going to have you kind of brainstorm what would be a reasonable input and output to a function. Just how long would you like to give them for this one?
I'll give them 180 seconds.
Awesome. So in that 180 seconds, if you want to go ahead and please answer those questions in there. What information would the function consume as an input? What do you think? And then what information would it produce as an output? There are no wrong answers, but we are going to kind of, just like good modelers do, we are going to kind of, narrow you down to where we need to. All right, Jess, you want to send them? We'll do 180 seconds.
There you go.
Awesome.
The other room's taking their time.
Yeah, no worries.
A quick question then, while we're waiting.
Go ahead.
So the students don't actually have the tumble buggy, right? Or do they? Because it's not an experimental, but rather computational activity, right?
No, it's an experimental activity. It starts the experiment. So they're going to do the lab with the buggy, with the physical itself, with a marker, with a physical receipt tape, and the auditory of hearing a tick every 2 seconds. So they're going to actually physically create a series of dots on a strip of paper, like the old ticker tape from years gone by, except they're the ones creating the dots. And then from there, we then start to analyze that set of data that they created from the real world and move it into a simulation. So it doesn't start as a simulation.
Okay, thank you. Then that makes sense.
I like to talk about is that the end goal is to produce on the computer what we saw in person to the best of our ability.
Yeah, basically it's using the old Feynman quote, that which I cannot create, I do not understand. So the goal is that they need to be able to recreate what the buggy did in reality on the computer screen.
All right. So I know that we had some information. I'm not going to talk for you though. So I know room 3 had some ideas about what this function, what information it needs to consume as an input. Room 2, did you have any ideas of what the function needs to consume as an input? Any thoughts?
We said time.
Time. Okay. Room 3 seems like a coincidence. What did you say?
You want me to go ahead, Charlie?
Sure.
We said the time interval in between each computation.
Okay. So the interval in between. So I'm going to just, you got that. So we have time or time interval. I'm going to take us back into, let me pull back up the, this slide here. I think I'm spoiled with way too many monitors at school. And so go home and one laptop. Oh, it's just awful. All right. So we are going to, this particular whiteboard and this, exercise the students engaged in to kind of predict the position. This is the key. This is the key right here. Because notice they predicted the position of the next buggy. If I know the current position of the buggy, I can determine the next position of the buggy. I'm gonna always follow some sort of pattern. My students here said that each movement is always going to be similar to the mean. And when they expanded upon that, they're like, oh, well, there's a mean value that the position seems to increase by each time. And this is the key for them. This is what they need. And so, sorry, I lost my stuff. When we are working through this, I have no idea what happened here. I'm going to stop sharing.
I tried to make it bigger.
Oh, you tried to make it bigger. Okay, well.
Did it not make it bigger?
Yeah, whatever. I thought I did something. I'm glad it wasn't me. Okay.
Is that bigger? Or is that better or worse?
It's no. All right. So this is the key here. So notice time is nowhere in this. And when I can tell you when Jess and I first starting in, it's like, well, wait, we have to have time. We have to have time in order to determine what position is. But the key is if I know where the buggy currently is, or even better, the computer simulation knows where the buggy currently is, and we know by how much the buggy should move for every tick, we can determine where the buggy should be at the next position, and the next position after that, and the next position after that. Because what they're doing in the computer is iterative, and they can repeat this process over and over and over again to move the buggy. And so what we wanted to show you is how we get from kind of this spot on a whiteboard using information what the students had to now taking them into determining what goes in the computer. And this is where that function design, the link that Jess put in earlier, I'm going to go ahead and it is in the chat. I'm going to go ahead and pop it in there just one more time, just in case. Unless Jess beat me to it.
I didn't. I'm trying to do something. I got 18 windows.
There we go. No, you're fine. So I'm going to go ahead and put this up here. And actually, I'm going to walk you through kind of what our students do from just that question that you answered in the breakout rooms. Let me pull it up on my screen. This is super fun. Okay, so, there we go. Perfect. Are you going to go ahead and do you want to type?
I'd love to be your hands. Go ahead. Tell me.
Okay, so we're going to start with this box that says physical interpretation, because these are the questions that you just had. So if I know what the current position is, if that's my input, that's what the computer's taking in, I can produce the next position. So our input output is super simple. We're going to start with the current position, which for our students, they measure in centimeters. And then we're going to, the function is going to produce the next position, which again is going to be measured in centimeters. And so from that, we're going to, every question underneath, the way that this has been designed reflects back on those 4 questions above. And actually really just the 2, what the input and output is. So if I look, I'm creating a contract with the computer. This is all of these I consider to be additional representations for the motion of the buggy. So we're going to write a function. The function name we've given it is nextx. One of the big reasons that we use this functional language is that there is a lot of research that shows that, and when students progress through algebra, functions is where it starts to break down, where they start to have difficulty, where they start to have, it starts to be a little bit more of an issue for them because they're thinking a little more abstractly. So my students have started functions in August with me. They haven't even gotten there in Algebra 1. So for them, it's going to be a lot easier for them to kind of progress through. Okay, so we're going to, if I look there, we're still talking about functions the way we do mathematically. A function name is nextx. We have a domain, our input type. If I look, the input is current position. The 3 input types that my students have had a number, string, and image. And they just came out of a lab where they put numbers for position on a table. So it's easy, they know that that's a number. And again, if I look at output, the range or output type, if next position is also going to be one of those numbers on their table, it's going to be a number. And then so the function design already has a contract. Purpose statement is for the human. And I can say that the function consumes input would be current position and produces output, which is next position. And here's where we can stay really simple. And actually, Jess, I have put in, I think I did a tiny URL that actually has, I'm going to put in here in the chat, that has some pieces filled in for people. So I'll give that to you all as well. This function design is something that they fill out, but you know what? We're going to let you kind of cheat a little bit, since I know Jess doesn't write examples all the time. And so, you know, sometimes we can kind of go past it.
That
Hmm?
was years ago.
Okay. But if you want to go ahead and pull up that particular link, the tinyurl.com/cmpf-sneak-peek, it should pull up a pirate. This is a language that we use in computational modeling and physics first. But it's going to pull up some starter code. There's some stuff done in the background for you. There are some directions as well. One of the best things I love about computational modeling and physics first is it forces my students to read directions. And so they are going to spend quite a bit of time really learning how to read directions carefully. So I'm going to let you, should we give them some time to kind of fill in some information? You are welcome to set the initial position of your buggy, whatever you would like. But at any time you see, actually, I'll let you read directions. I don't know what I'm reading to you. I don't do that to my students. What you do? Jess, do you want to scroll in and type in the contract and purpose statement that we put in the function design already? Is that what it is on the screen?
Done. Don't tell Ben I'm doing that in quotes and capitals.
Purpose statements are for the human and not the program. So
I know, but you
Yeah.
know, syntax.
yeah. So you know what? And I know some of you are probably typing, but in case you're lost, we can talk about examples here. If I look at my examples block, the examples are going to work the same way that I told the computer, actually told the function design when I did that physical interpretation box. So in the parentheses, mind you, our students have done this, I'm going to put inputs. I know that the input is current position, and the type of input I'm going to put in here is a number. So I can pick any number that I want to use in my example because I'm picking an example number. Awesome. And then the output is going to come after the is. That's the calculation that I want to give the computer. So if I know that buggy is already at 5, I want to give the computer a calculation to find the next position. And let's say that I saw in my lab that the buggy moved for every 2 seconds. I had a really slow one. The buggy moved 35 centimeters every 2 seconds. I can put in something as simple as just typed and say next x of 5 is 5 plus 35. And so I can fill out the rest of my examples just using example numbers like that. Students, when they do that, my students like to use the numbers that they had on their data table. The only thing I have to remind them of is that their data may not have been perfect. And I always say their data is experimental. I'm looking at the computer, is really going to be more theoretical. This is going to be a little bit perfected. Their data isn't perfect. And Jess is demonstrating there that we can do either way. I can give the calculation, or I can do the calculation. I like to tell my students, why would you have the computer or a calculator why would you do the math and you wouldn't enter it in the calculator? Let me do the math. 35 plus 5 equals 40. I wouldn't put it in the calculator. I would put in 35 plus 5 and then hit enter and have it do the work for me. So I encourage them not to necessarily show me, the answer all the time, or show the computer the answer, but tell the computer, it's been a long day. Tell the computer, let the computer do what computer's good at. Thank you, Charlie. It's been one of those days that ended with me giving the lecture about semester exams, so that's right. All right, so if I come down to you, I'm gonna let just put one more example and I'll make him type it. He can choose a number.
Ooh.
Oh, it's beautiful. Okay, so then if I come down to my function block and I tell the students, this is our generic one, and this is, you can see as you work through the function design, this or two. So when I come down to the input, now the input is not an example. It's not an example number. It is the current position. And so they have to think of, and this is where we can brainstorm as a class as well, they have to put in what would be, how would I represent that current position? And quite honestly, they can put in a lot of things and put in what they want. And usually in this one, I do let them put, so I get a lot of like curve position, CP. I don't usually get them to X quite yet because they can put it where they want. So they know if the input is current position, they're going to, if the computer knows the current position, the computer is going to calculate the current position by doing the same process that they did in the examples. Awesome. Do you have everything? Do you hit run and see if yours works?
Well, I should probably give it an initial position.
Oh, you probably should. Yeah.
Let's make it with 5s. All right.
And notice we told the computer that we put room 3 had that idea about the interval time or time interval. We're starting them off with something that matches and mimics their lab. So it's every 2 seconds. So right now the computer is just recalculating the position every 2 seconds. And this is where, do you want to go back over to the sneak peek presentation? We'll kind of go back to, because I know I put some information in there we can go to. So we do have, just like we have the students do for most everything, we do have them whiteboard their function designs. I can share this presentation with you if you really want. You can see that my students made some mistakes, math mistakes in the function design too, which is always a fun way. If I make a math mistake, the computer, especially using the Pirate programming platform, is going to give them some feedback that's going to help them figure out where they might have gone wrong. All right.
And I just want to show you one thing real quick. They actually provide, the program actually will provide the output table. So if we ignore the time axis, tick and position should match up almost perfectly with their output data from the lab. There'll be a little bit of fuzziness with their actual numbers compared to ours, but this is verification that it's doing what they expected it to do, which is much more encouraging for them than when you as the instructor just goes, yeah, that's right. They don't even need you to say that's right because they're like, oh, look, it matches, which is actually
and one of the coolest things to see is having students who, they do their lab, they can look at their table, but the table in the graph don't have as much meaning to them as when they look at the screen and the computer in the car moves and I see kids go, oh my gosh, I'm really excited because the car did what they expected it to do. So I can reassure you that we don't stop. The process doesn't stop there. They do refine. You can kind of see here, Jess, if you want to monitor chat, here's what I'll do. I will do this. Yeah. And then let you take it. Okay. So they do go through the process where they kind of refine what they have. We started with every 2 seconds, and you can kind of see this is my students reproducing what their receipt tapes would look like every 2 seconds. And then now if we change that delta T, that times interval, to 1 second, what would happen? You can see they've kind of located that there must be some positions in between, and therefore they're not going to move the buggy as much. And then we can kind of keep repeating that so they can get the idea. And the goal of doing this exercise is for them to understand that the amount they have to move the buggy by has something to do with the interval time, something to do with that change in time, that delta T. And so that's where this whole activity, this portion here on the whiteboards, we get this idea that it must be velocity times delta T in order to figure out how far they have to move it. And from this, we eventually are going to get that smooth piece that you saw in the video that we started out this process with. I want to note that in Computational, we haven't even gotten to a graph yet. They have recreated the motion before they've developed a representation that includes state diagrams, it includes tables with predictions, it includes these receipt tapes, it includes a computational representation, it includes everything that they have in their function design, their function, their contract, their examples. All of that has been representing the motion of the buggy before we've even gotten to a graphical representation. And that is really where the computational modeling in physics first takes kind of a different tact from that, the physics mechanics would do.
So
go ahead, Jess.
Scott had a question in the chat. He says he's not sure if he understands the purpose of the contract, where we're just telling it that the input and the output are both numbers. And to a certain extent, you're absolutely right. That is part of what's happening in the contract. But more than that, what's happening in the contract is the student is identifying to themselves that they put a number in and a number comes out, as opposed to assuming that. So
Okay.
the contract with the computer saying, I'm going to provide you with a number, you provide me with the requisite number following the rules I'm going to give you later. But the other part of it is the purpose statement, which is that hashtag, which is how we do a comment. So you talk to the writer. So the human sees the function is going to take in current position, which I will represent as a number, and it will produce the next position, which will be represented as a number.
See, that part makes sense to me. I guess my question would be like, when would that ever not be number to number?
When it's number to image, when it's
Okay.
Boolean, so we're doing it right now in a very, very physics way.
Okay.
But the students will have done a unit where they manipulated images, and they can move objects within a field to create flags, and the output is actually the image of the flag that they're producing.
Okay.
So
Gotcha.
we have to put in the coordinates, which are numbers, and then the computer puts them in the appropriate place and outputs the image.
Okay. Thank you.
No problem. Because we're trying to teach both sides of this. We're trying to teach both programming and physics. So that would fall under the programming side of data types come in multiple forms, and we have to know what form we're using so we know how to use it.
Or at this point, they've done things like calculating the area of a rectangle that take in the input of two numbers, not one, to produce a single number. And that idea of how that works and how it relates to functions that they're already familiar with is really powerful for students.
I will say that with if you want to, I know Jess said the computer science and the physics. I do bring in sometimes the algebra if my students really have trouble. We'll draw kind of the old diagrams of, here's my domain, here's my oval, my domain, it's number, and my range is number, and I have, one specific number is going to produce, produces only one answer over here, and I can kind of bring in those ideas of what domain and range is algebraically, using the contract as kind of my way in to that, before my students ever get to an algebra. And so it's funny, when I started doing this, the algebra teacher was like, what are you doing? Because I am having a much easier time getting that domain and range across. So it's kind of there's some sneaky algebra written in so that students have more practice with some of the things they might struggle with later on.
Which is actually a nice segue into the why pirate.
Right. So
Go ahead.
This is the most common question that we get. We're not using Python for a very specific reason. Pirate was designed for student use, and actually it was designed to use really for us. Bootstrap, which was part of the initial grant as well, started out using Racket. And really, when they made the transition over and included us, that's where this language was really started to be built out. So the whole Pirate programming language and the platform that is used, which is Google-based, by the way, which means it's nice, so we don't have to download anything onto student devices, all kind of came about because of computational modeling physics first. The syntax is Python-like, so I have had students that have then kind of springboarded into using Python to create whatever. So it helps kind of give them that, that boost. But it is designed for student use and for high school student use. And in fact, I know that Bootstrap even uses it with like 7th, 8th graders for some very beginning algebra stuff. So it is very user friendly for students. And one thing I absolutely love, it does not give them answers, but when it gives them, and I'll say a little bit later when we talk about the error analysis and problem solving, it puts the impetus on the kids to analyze their errors and figure out what's wrong.
And it follows all of the rules of algebra. Unlike a lot of other programming languages, you can fudge things. You can say that x equals x plus 2. You can't do that in Pirate. X can't equal x plus 2. It's not possible. Just like in algebra, x can't equal x plus 2. So next x can equal x plus 2, but x can't. And so it follows all the rules of algebra. If you have a function defined in one long string and you wanted to input it in as a substitution, you could literally copy and paste everything there and put it down below, and it would work as a one-to-one substitution, just like it does in algebra. You know, if you say that x equals, y plus z, and you replace everywhere you see y plus z with x, or vice versa, it works just as well. So there's a lot of commonality with learning the algebra while you're learning this, because we're not breaking rules of algebra because we're programming. Whereas in other programming languages, you can get away with that. If you're in C or whatever, you can say that x plus plus, and all of a sudden you got, well, that means x plus 1. Well, not to anybody who's ever done algebra, only to somebody who's in the know of how to program in C. Whereas in Pirate, you would have to say x plus 1, because that's what you would say in algebra class. So I'm sorry, go ahead.
No, you're fine. So there are a few advantages. Some of these are intentional. Some of these we found out from using this with our students. So I kind of want to talk about, we're going to talk about all of these. The students have the ability to think in differentials. So there's thinking in smaller bits. We're increasing user functions. We have some immediate testing and visual feedback, which the visual feedback is amazing. And then, my favorite on here, last but not least, is having students do more error analysis and problem solving. And when I say problem solving, not just solving physics problems, but actually having to kind of like think things through, to kind of come up against that issue or that wall and be able to work through that particular problem. Speaking of like the focus on differentials, the focus in this, and I would say the most important representation that we have throughout these particular resources that we found really came to the forefront when we were writing it, was a focus on motion maps. That this made motion maps looking at like, how much does this object move for every tick? How much does it move for every second? Being able to think in those time increments. This was a huge shift in thinking from physics mechanics, that motion maps became more and more important. And actually, I find students using motion maps more and being able to understand what they mean, because they are really specifically looking at motion maps, because this is exactly what the computer is doing for them. It's making if I look at that, when we put every 2 seconds had the car move, it's making essentially a motion map of the car every 2 seconds. If I make that time step 1/20th of a second, and it's making a motion map, it may not be so easy for my eyes to pick up, but that's what the computer is recreating. Jess, anything to add? Oh yeah, you said order operations. Yeah.
Yeah, I threw it into the chat there, but yeah, Pirate does not know the order of operations. So if you have 3 plus 4 times 2, it doesn't know what to do, and it'll give you feedback. So you have to tell it you want it to do 4 plus 3 parentheses and then multiply it by 2, or 4 plus parentheses 3 times 2, because it doesn't know. And frankly, the students don't always know either. But this forces them to know, I want to multiply, so I have to put this part in parentheses, then whatever that is, add it to something else.
I just realized this video doesn't work, but looking ahead, if I'm thinking of the students looking at things differentially, this is something that they do in Unit 3, where we're trying to determine basically how to build the area under the curve for a velocity time graph, building this idea. And they're working with a pace car. Just to give you an idea, the pace car is moving. We are controlling the pace car in the background, and the students are controlling 3 cars. They're trying to figure out what I Would I figure out displacement by using a current velocity, by using the velocity in the next tick, or using an average? So the students have to kind of build this on their own. And so having this visual output makes it very clear to them. We can do a graph and I can show them, have them do the rectangles to kind of mimic or to reproduce the area of the triangle, but having them do this on the computer, they can see, you know, one car is falling way far behind, one car is moving ahead, but I need to do something different. So here is this error analysis piece, just to give you a like kind of a snapshot of what the computer is telling them. Pirate gives feedback. We don't say it gives error messages, it gives feedback. And you can see that it gives very specific, would be feedback from examples, comparing the examples to the function. I should say the function is the left side and the right side is what you're calculating an example. But you can see that it's very much telling them what is going on here. When it brings up feedback from anything within the function or the code that they're writing, it's going to give them not only the line number, but it's going to highlight what's wrong. And then it's going to tell them kind of not what to change, but give them examples of things that might need to change. Like you need to look before the highlighted area. Saying things like an addition and multiplication operator are on the same level. Use parentheses to group items together. So the feedback that it gives them encourage the students to look a little bit deeper. We're also able to do a lot more challenging scenarios with students. One of those looks like I need to get working again. Okay, but you're looking at, like on the left, this one is something using the acceleration of free fall on the moon. Students are collecting data, and you can see that it is a video from Apollo 15. The dots there are following the hammer and the feather down. The circles are programmed by students. So they are, you know, using this data to determine the acceleration of free fall on the moon, and then writing a function that uses that, and then trying to recreate that motion. The one on the top right is my favorite. It's our self-driving car. They're programming the braking system of self-driving car. So they have to determine like what information does it need to take in. And in this case, it's taking in two numbers, the distance to the stop sign and the velocity of the car. And then what it is producing is a Boolean, either true, brake, start the braking system, or false, don't engage the braking system. So this is a really good one for them, that they have to get to, you know, that equation, the VF squared minus VO squared equals 2A delta X. They're actually really figuring that out on their own. So I don't have my students use equations at all in my class, but they are figuring this out because they're drawing a graph and they're coming up with, how do I figure out that area? And then they're using it on the computer. So they're doing much more challenging, because Pirate's kind of helping move that along. That visual output is very, very, it's very motivating. And then the bottom right, this is one needs to be fixed, is a drag race for the students to look at the forces acting on a car. They have to get it moving. So it has to have some thrust. It has to have some drag because of air resistance. So we're, you know, not neglecting air resistance for a big portion of one of our units. And then, you know, they have to get their car to stop as well. So computational modeling in physics first, because we're using that, just the, you know, the differential motion, and not necessarily like looking at the whole picture equation at one time, but just, you know, can I move it this little bit? Can I move the position? Can I change the velocity? They're able to do something that is much more challenging. And I do want to say, I'm going to move us along here because I want to respect everyone's time and give you time for questions. But we thought that this would be part of the model deployment process, and it really has helped the computational piece become part of both the development and the deployment part of the modeling cycle. So we're able to use, you see it was used very early on with the buggy, but actually when we start coming back, we're able to develop some models using Pirate to develop the models. All right, so if you are interested in next steps, one of the wonderful things, Jess and I are going to be working together in a distance learning course in the spring. It's starting in January, running through April. So that is Tuesday nights, 7 to 10 Eastern time. So, you know, if you're in Arizona like me, it's sometime somewhere in there. And then we don't have any summer workshops scheduled yet, but I'm going to put in a plug, and we'll put in a plug here in just a moment. Let's see. And actually, you know what? I'm going to go through. I want to make sure that we include what information AMTA has left us, and then we'll come back to questions. So if you do not following AMTA on social media, I highly encourage you do. Information is put out all over the place. The Science Modeling Talks podcast is amazing. Jess and I have done an episode there together. You can hear us talk about our love of football, or lament, because I'm in Arizona. But feel free, please, take a screenshot, write any of these down. Feel free to reach out to us, and we can give you this information as well. If you are interested in a modeling instruction workshop, please contact us, engage@modelinginstruction.org. On the modeling instruction website, if you go to professional development, which may be how you got to this, there is information already cycling about summer 2025 as well. So you can look at our professional development and see workshops by discipline or area. And those distance learning courses, those will be on there as well. So if you go to distance learning courses for the spring, you will see the one that Jess and I are leading. And I do encourage you to fill out that sneak peek survey. And I am going to, let me see if I can pop this into the chat so you can get that as well. We do like having your feedback so that not only can Jess and I make things better. Oh, thank you, Jess. That's much better than my non-link. Okay. But this helps us make things better. This also helps AMTA provide more information. All right. I will leave that up there, and we will open the floor to whatever questions you might have.
Are there any thoughts of ever doing a momentum unit?
So, yes, and
we've been talking about that since 2017.
Yeah, but we are currently working on a unit 6. So I will say computational modeling right now has qualitative energy is our first unit, constant velocity, uniform acceleration, balanced forces, unbalanced forces, and we are working on one that's going to be fields. So
gravitational and electromagnetic?
Gravitational and electromagnetic. Considering it's created for 9th grade, it will focus more on the gravitational electric fields, more so than a magnetic field, just because, cross products and 9th graders. Yeah.
Sweet.
I can't imagine teaching my 9th graders right-hand rule. I don't know how that would go. Probably not well. So, but it'll focus a lot on electric field and gravitational fields. Mm-hmm. So hopefully we should have that done, and with a beta version ready for the summer.
You're aggressive with the beta version. I'd call it more of an alpha version. Maybe an alpha 2.0. I wouldn't go so far as to say it's a beta.
Alpha 2.0. Okay. All right. Well, if you have questions, Jess and I can stick around for a little bit. Yeah. But feel free to pop off of there. Please do fill out the survey. You can, if you want to, Jess, do you want to put your email in the chat as well? I'm going to put my email in there. If you have questions, feel free to reach out to me. I'm happy to answer those. I'm sure, I'll speak for Jess. I'm sure he's happy to answer questions as well.
I'll answer questions.
Okay.
And if I don't want to answer it, I'll just forward it to Melissa.
We've been working together on this for a really long time. Uh-huh.
I have 2 quick questions, if you don't mind.
Sure.
So is this sort of the first sort of of its kind is a computational modeling development within the modeling instruction community? And
yeah, this is the first one. I hope it's gonna be. We've been talking for a long time, for years, about branching out. I think it's gonna happen. It's a lot of it's grant funding. I don't want to throw out ideas out there. I know I've said several things, but there's we would love to bring the computational thinking piece into a lot more content areas. And there are some thoughts on what exactly that would entail. And when the grant funding does happen, I'm sure they'll be AMT will be reaching out to more people to kind of try to get that going.
On that thought, though, one of the other things, and we talked about this early on in the development of this, we don't want to create something just like something else that's out there, because we don't see a point in reinventing the wheel. So unless it is dramatically different and we believe better than what's currently out there, we're not going to put our effort into that. So, for example, there's a lot of PhET simulations out there with a bunch of different things that can be very, very useful. But you'll notice our stuff isn't set up like PhET, because our goal is different than what PhET's goal is. And the same thing is
That
true
makes sense.
with like chemistry. PhET has some great stuff on gas laws, which frankly with Pirate probably wouldn't be easily done with our level of programming knowledge, because you'd then be trying to move 18,000 particles and your processor wouldn't be able to handle that. Whereas PhET already has a lovely simulation. Just use that.
I would say if I could make a prediction of what will possibly be the next kind of iteration of this, it would be something to do with data science. And I've kind of, I'll say it, I've thrown out there, I think that environmental science and data science would be an amazing combination. But I could see data science being the next one just because of the way that it seems like grant funding is going.
Makes sense. And then another question, the other question I had, so I'm new to modeling instruction. I'm a grad student. So the modeling instruction is based on the quite extensive research from the past, right? And it's well established now. How about the computational modeling specifically? Is there any sort of research going on, or has there been specifically within the framework of like modeling theory, going back to Hestenes?
Right. There was. Jess, was that what Rebecca wrote her PhD thesis on? Was the part of the grant? So yeah. So Rebecca used to be formerly, she's currently with PhET. But she was part of the original grant and did a lot of her PhD work looking at computational modeling and its efficacy. Colleen McGowan Romanowitz, who is senior fellow with AMTA, has been part of the grant since the beginning and they've done some research. As part of the original grant, we looked at not only we looked at a few things. So they used the force concept inventory. So we looked at how students' concept development in physics. We looked at function development. So they did kind of a function, like a mathematical functions pre and post inventory for both students and for students and teachers. We also looked at I'm trying the best way to word this, like their comfort level with the computational piece and with doing some code. So the research went into kind of those areas. I also know we looked at kind of like how students went about solving problems as they, not just the physics problem solving, but like, coming up against issues with their code and how they kind of worked through that piece. So all of that, there has been research done into all of that. And I know that research, Rebecca and Colleen have done some publishing of said research. Off the top of my head, I'm not sure. I can't think of places where it has been.
I think it's on the Compadre website.
Is it on the Compadre website? It probably.
Compadre on the APT, I think.
Okay.
Yeah,
I can find it.
He was one of the original partners, so it has a lot of the information.
Thank you very much.
You're welcome.
Very helpful.
Appreciate it.
Questions out there? Jess has lingering comments.
I said I know that Charlie has questions because Charlie always has questions.
Oh, I do. But I have one that's like slightly off topic. I'll ask you later. That my students have been bringing up, and I'm just interested if you know the answer.
Go for it.
It is so I have my students also use ticker timers.
Okay.
And they're wondering about the history of the ticker timer versus the motion map. what came first because they're so similar in what they do. Did the idea of the motion map as a representation come from people working with the ticker timer and then seeing that it could create this representation on paper that helped understanding of motion? This.
Ooh.
I believe the ticker timer came first, but if you told me it wasn't first, I wouldn't argue it. So
So
my intuition, not my knowledge, says ticker timer came first.
Because ticker timers
I'm a
have been
little bit
around
waiting.
since like
Yeah, it's been around.
way
Yeah.
long ago, right?
Yeah,
Weren't
well,
they weren't they in use in like at least the 70s back then? And
in earlier than that, I
Yeah.
know that modeling instruction in physics really got its birth out of the old PSSC physics, which came out of the Sputnik era response the US had to Russia getting to space first. So the ticker timer was big back in the PSSC. And I'm pretty sure that Malcolm Wells and David Hestenes and Schwackhammer, when they were pounding out what modeling physics was going to be, and the motion map kind of came out of there, I'm pretty sure it was based on the idea of the ticker tape with the dots is really great, but I think we can take it one more step. And that's where the velocity vectors got added in, because it's like, hey, we could do this just a little bit extra, which will give us a little bit more information. So if I had to guess based on my understanding of modeling instructions beginnings, which really is just an offshoot of PSSC. And the goal of modeling from day one has always been to don't let happen to modeling instruction what happened to PSSC, which is when PSSC's funding ran out from the NSF, training went away, and it just kind of died the slow death of the new generations of teachers didn't know how to use it. Because, you know, Bob was my cooperating teacher, but I went into a school and the first thing they showed me was the physics textbooks were PSSC, and they were very proud. And I looked at them like, I don't know exactly what I'm supposed to do with this. And
Melissa, I have a question for you.
Oh,
So this is my second year doing the curriculum now. The first year I was like learning it. So I was like very heavy in the use of the worksheets, but I found out students like kind of got burnt out from the curriculum set up like that. And I've been moving the worksheets more to whiteboard or other activity experiences. And I feel like looking at your student whiteboards, you're kind of doing the same thing, that you're taking the ideas of some of those worksheets and creating whiteboard activities for them. Is that right?
Yeah, absolutely when I can. I mean, I like to do more of having them do whiteboards. I think you know, over the past 3-4 years, I found more kids just like to take the worksheet and just copy off whatever everybody has, which means I'm not seeing their thinking anyway. I'm seeing somebody else's thinking copied 50 times. So I have been doing a lot more with whiteboards. I like to do a lot with having my students write. So having them actually explain their thinking. So we might do an entire activity, and instead of you know, a worksheet, they're writing me a claim evidence reasoning of what exactly was going on and making sure they're using evidence. So I'm doing what I can to kind of avoid the constantly making copies on things. And there are a lot of the things within the resources. You can kind of use your best judgment. A lot of those things I can kind of move to making it something that's almost completely paperless anyway. Like I'm going to do in unit 4, we had the ball sand fan simulation where the students kind of really get this idea. We build this idea of sum of forces. I do that, and I have the students draw things in their notebooks and on whiteboards, and that's what they turn in. They just show me a picture. So rather than using the worksheet, we work through it. They kind of work through it in teams, and I have slides so I can kind of prompt them what their next piece of conversation is, and I can just cycle the room and kind of talk to the groups and figure out what they have, and they're putting information in their notebooks while they put it on their whiteboards, and it works out for me.
Yeah, and another thing now that you're saying it that I like doing now is with the worksheet problem, that I actually have them cut out a problem now from their worksheet, put it in their notebook, and this idea comes from that mathematics thinking classroom. I have them write notes to your future self.
That's a great.
underneath as a caption of a particular problem from the worksheet. I found that gets it a lot more buy-in and work
Yeah.
and out of the worksheets.
Yeah. No, I know. I think I mean, I started teaching probably the same time you did, Jess. I think I'm a year after you, but like watching, students change, and I am a student of an original modeler. Like my teacher, my high school teacher, took the modeling mechanics workshop summer of 1993, and so I was in her class the next year, and so I've seen a lot of these problems since I was in high school. So sometimes look at it and go, you know what? I don't want to look at one more of this problem. I need to kind of shift things just a little bit. Um, and I've watched my students, the way that they have to be motivated is a little different. So, you make modifications. The resources are, we're able to change the resources. That order that we use them in, the order the concepts are developed, that kind of we suggest to be followed, but worksheets are there to kind of help facilitate the lessons, and you can kind of do with them what you need to fit your classroom.
Yeah, it's the pirate code. They're more of guidelines than actual rules. But we would recommend that you do the content sort of in the order of developing the ideas in the order that's laid out. But how you get from point A to point B is kind of your area of expertise, because you know your kids better than we do.
And I would also say a big thing about the curriculum is that it leaves the summative assessment piece really to you as the teacher, unlike other AMTA curriculums that have a lot of summative assessment resources. And I think that's been an interesting journey for me with like that backwards design mindset. Like, all right, here's the curriculum. What's the goal that it's building up to? What's that kind of performance assessment that I'm wanting them to do at the end? Now, how am I using these activities to kind of scaffold them up to that point? And that thinking as a teacher that you have to go through with the curriculum, I found really valuable.
Thank you for that. Where can we send your $20? Because people have been asking us to write quizzes and tests for the longest
No,
time.
I think if anything, what would be
And-
helpful is like possible like performance assessment ideas, but I wouldn't give them any more than that.
Right. Because I think there's, Jess teaches in a public school. I teach in a public school, and a lot of public school districts have really gone to a specific way that they want teachers to assess. And so putting in, I'm like, why am I writing quizzes or tests when it's going to end up being something that comes down from district? Like it. Yeah, we have bought that one for years. I'm like, I don't want to write quizzes and tests.
Yeah,
Those
we
are, I
fought
think,
that,
very
and we
critical.
fought the answer keys, because
Huh?
we fought that and answer keys.
Oh yeah.
Every year in a workshop, everyone's like, well, did you do the answer keys for that? It's like, no, but you do. And if you don't, then we didn't do our job as workshop leaders, making sure that you were prepared to do this. So you create the answer key for yourself as we go through the work. And then you need to create, because a lot of the questions are ambiguous from time to time. It depends on your interpretation of the question, how you want to address it. And so with that in mind, there is no answer. There's appropriate responses based on the evidence and the assumptions made. But so like the lab, for example, like, in my class, I have cars that go in the positive direction and the negative direction. None of my cars start at 0, but that's me. If there's a teacher that wants their cars to start at 0 and all go in the positive direction for this introductory lab, more power to them. That's their choice, and they can certainly do that. But you can't make an answer key that actually has the power to do everything that the materials are designed to do. Take care, Bob. It's good seeing you again.
Likewise. Good luck.
I'm gonna head out too. Thanks a lot, everyone.
Here,
Thank
Scott.
you.
All right, Charlie, I know you got a deep question somewhere deep down inside that you want to know the answer to.
It's been good. Like, I love the
Awesome.
curriculum, so.
Awesome.
I would say
love hearing about that.
I'm in a different situation. So I teach it in a physical science class.
Okay.
So we do a physics unit from the curriculum, and then I do a chemistry unit. And interestingly enough, the chemistry unit heavily uses PhET simulations. And then we go back to creating our own simulations in Pirate in the physics unit, and it's back and forth as the year goes. And with that setup, I'm essentially able to do the curriculum with my honors group in that time, but I'm able to only maybe do, I would say, probably 60% of what's there with my regular students. With the time, I also have to give the chemistry.
That
throughout
sounds
the-
right. Yeah,
yeah.
that sounds about right. I mean, we've taught, teachers from all over the country in very different scenarios. Yeah, it sounds like you're right on pace with like kind of what people are saying. We've had
Cool.
there's some really odd schedules out there. Like,
yeah.
I like the idea of kind of going back and forth. But yeah, we've seen some ones where people only see their kids like every 3 days. Like, I don't know how you would do that. I don't know how I would survive.
Yeah.
Like,
And
I can't
like
finish
I
my
said,
thought from one day to the next.
I struggle on Monday sometimes with them forgetting things from Friday. I don't know how you'd
Right.
handle it. Like you don't see them from Tuesday until the following Monday. It's like,
We got to today identifying that the interactions between objects on a system schema are forces. And I got them to agent object notation, but I didn't add the fact, I didn't do like F by E on, like, oh, that's going to take some doing and come back to that tomorrow. Yeah.
yeah, I'm about
It's
there.
hard.
That's where we are today. Tomorrow we'll probably hitting system schemas for the first time.
Oh, nice.
Because we don't do energy first.
Yeah.
Because my school is, top down.
I wouldn't say threw a fit, but I really like pushed hard last year, and the entire district switched to energy first this year. Yes. I got the chemistry teachers on my side. I'm like, look at how good your kids are at energy. Come on.
I keep trying it, but they want us to start with matter and interactions. So we
Okay.
start with conservation of mass, which is nice, but
Yeah.
So I think when I'm teaching the energy, it's more about the philosophy of that we communicate through representations more than I care they learn anything about energy.
Right.
I want them to
Right.
get comfortable with us telling a story with a system schema. I want them to get interested in telling a story, just like they write a paragraph with an LLL chart. That's what I
Yeah.
care about. As far as the energy goes, I care less what you kind of know about energy when everything is said and done. And that's like sets up that idea of how important I think the representations are throughout the rest of the course.
Yeah. What's nice is like, because there's such a focus in modeling instruction on representations. Like I get kids that I'll go past. Our classrooms are built with like giant windows, so I can go past and look at them. And I like to sometimes in my prep, I'll go kind of peek in on the science department and see what we're doing. But I can see a lot of the kids. It's like that their mastery of representation from having such a representation heavy physics course freshman year. It's like, man, look at it. I can see that they're drawing in their notes, and they're drawing diagrams of everything. They'll do whiteboards because all of our classes are supposed to be modeling instruction, but like their whiteboards, and the kids get it really fast. And hearing from the chemistry teachers, like, man, they got particle diagrams really easy. It's like, yes, they knew representations is the way to go. So rather than, you start with biology first, sometimes it's really hard to build that. There's not a really good way for them to do that as well when we're talking something where the diagrams are very specified.
yeah, and there's not a lot of gray area.
No.
You
No.
have creativity. You just
Yeah.
that's what you
Darn
got.
biology.
It's true.
Yeah.
That's why physics is awesome.
Right.
Well, thank you.
Thank
You're
you.
welcome.
Have a good night.
Bye.